Hey guys, it's Jimmy here. Today we're going to talk about oscillators. Oscillators is an important concept in physics because it acts like a transition between classical mechanics and quantum mechanics. Much of the conclusions drawn from the oscillators can make contributions to quantum mechanics. However, all these conclusions are based on classical mechanics. Okay, in this video, I'm going to talk about several oscillation in different situations, including the easiest harmonic oscillator and also forced oscillators with damping. Okay, first I'm going to talk about the most simple situation, the harmonic oscillator. I think this part should belong to the field of maths because most of the operations we do here is solving differential equations and other mathematical operations. Okay, so for harmonic oscillators, we have its equation of motion is a second order differential equation with constant coefficients and is also linear. Okay, I'm gonna explain these terms one by one. So by the term second order, it means that the highest order of derivative is second. It will not contain terms like this. So this belongs to order 3 and it exceeds the highest order. Okay, by the term constant coefficients is kind of easy to understand. It's just that the terms in front of the number in front of the derivatives should be constant. Means that if we have an equation of motion like this, A, B, C, and D should all be constants. Okay, by the term linear, we mean that we should only have adding or multiplication mathematical operation for the variable x. If an equation looks like this, like plus sine x equal to 0, then it's not linear because it has an operation of sine in front of for the variable x, which should only contain like adding or constant. Suppose C is a constant. Like we should only have operations like adding and multiplying. We should not have sine or other log or log and ln that sort of operations. We should not have them. That makes the equation non-linear. Okay, so let's consider a very simple situation. Here's the diagram I drew, and it's a block with mass m hanging from the ceiling by a spring. With a spring constant is k. It has a mass of m, and when the block is at rest, its position, we have a coordinate system, like a vertical coordinate system. We call it x, and let's change it to another color. Okay, we call it x. And when the block is at rest, meaning that the force exerted by the spring is equal to its gravity. When that balance is reached, it's at the origin. Its position is at the origin, means it is at 0 over here. Okay, so the block with dashed lines is when it was at rest. Okay, when it was disturbed, or somebody just pull it down by some distance and it will bounce back up. And without the friction, it will just be be doing SHM, simple harmonic motion, SHM. Okay, so we just grab a moment from this motion, like I drew with the thick lines over here. So it's at position x, right? It's got a position x. It's moving up, obviously, because it's moving up. And however, the force it receives, it was acting actually like against its moving direction. It's instead of up, it's the force it receives is going down. So in this situation, the force received by the block is always on the opposite direction of the direction it is moving towards. Like if the block is moving downwards, it's like when a block reaches here, it will obviously receive, like, because the spring is stretched, so it will receive this force pointing up. So the force is always against the direction of motion. Okay, with that being clear, we can establish equation that describes this motion. So at the position 0 over here, the force exerted by the string has already balanced the gravity of the block. Thus, when it was going up and down, the extra, like the displacement of the block, which is denoted by x, will represent the extra force that contribute to its acceleration. So with that being clear, we can write it as minus k times x equal to m times the acceleration. The sign minus means that the force is always in the opposite direction of its motion of the block. So we write as a derivative of the displacement x. So it's minus k times x equal to m times x double dot. Okay, and we will write this. We will just we can write the equation at this form. Okay, so in the last video I talked about the exercise in exercise for Feynman's lectures on physics. We have a similar equation to solve, which is over here, I think. Yeah. So it is also a second order constant coefficients differential equation, a linear differential equation. So we talked about a standard way of solving such equations, which is introduce a trial solution. So yeah, we use a similar approach here. So we also use trial solution, which is x equal to cosine omega 0 times t. The reason why we use this cosine function is that we noticed that after taking the derivative of the function twice, it will become the cosine itself. So in this equation over here, we can see that the left side needs to cancel out the right side, so it must take the same function to cancel out each other. So the cosine function and sine function are a perfect fit for such conditions. So we use cosine here. After we substitute the cosine omega 0 times t into the equation. Oh, by the way, omega 0 is to be determined over here. So after we substitute into this equation of motion, we will get this equation, and since it was this plus this equal to 0, and these parts are the same, so so omega 0 squared should equal to k over m, and that's how we find out. That's how we complete the trial solution. Next, we're going to delve into the physical significance of the coefficient omega 0. Okay, okay, let me write this out. Okay, so the solution should be x equal to cosine k over m times t. Okay, this is a solution. Okay, you can see it's a cosine function, so it should have the graph like this. It's a graph of x as a function of t. Okay, and since it's a cosine function, it's periodic, so it has a period of obviously. So cosine function is a period of 2 pi, and we add the coefficient omega 0 to it. So the period is obviously changed. When omega 0 times the period equal to 2 pi, so it has a complete cycle. Is 2 pi, so we can then find the period of the motion. So that's its significant. That's how its physical significance is reflected. You can see here. So omega 0 definitely have something to do with the whole period of motion, because without we're not considering friction of the air here. So if somebody just pull the string downward a little bit, it would just go up and down, up and down, up and down forever. So yeah, that's what I'm trying to pull here. So the coefficient omega 0 is can be helpful when we're solving for the period. Okay, so omega 0 times t equals to 2 pi, and the period can be derived from the equation here. It's equal to 2 pi times square root of m over k. We just substitute omega 0 over here, and yeah, we'll get it. Okay, the omega 0 over here is called angular frequency. We talked about in the last video. Okay, so here's this is a very simple situation for the harmonic oscillations. A more generalized solution to all the harmonic oscillations is takes the form of this, and this is standard way we just did in the last video when solving for this. So we are kind of concise here. We use both cosine and sine function over here just to ensure that there's no mistake, because sometimes the phase shift can change. There can be phase shifts, like probably in some cases the trial solution will take the form like this. Actual solution will take the form like 0 times t minus t0, while t0 is a constant. Okay, so in this case we need to expand this because cosine omega t t0 and it equals to cosine omega 0 t and cosine, and this is a constant plus sine omega 0 t sine omega 0 t0, and this is constant, and this is constant as well. So the solution will contain both the cosine terms and the sine term. Okay, so that's a generalized solution for that, and this is for harmonic oscillators, which is the most simple case of all. Okay, next we're gonna talk about another type of oscillations, which is called forced oscillations. In this case, an external force is involved. The external force will always be helping the system to do the simple harmonic motion, and thus its direction is always in the same direction with the acceleration, because it's helping the system to do the motion. So we slightly modify the equation. We add the external force term, which is F bracket t. The force is a function of time, because in a motion the magnitude of the force needs to change. Okay, so it's slightly different, and okay, so we write it into another form. Minus k over m times t plus f of t over m. Okay, so one of the most common cases is that you see in this case we're solving for x. So because we want to know the displacement over about time. So the force function is actually given. So in one of the most common cases is that the force is a sinusoidal function of time, which means that it takes a form like this. Okay, so we need to distinguish something here. This omega here is not equal to the omega 0, which we just talked about in the last case over here. It's called angular frequency. Angular frequency is something like it's like a property of the system. It's only depend on itself. It depends on nothing else except for the system itself. However, a force is external, so obviously the omega here is not has nothing to do with the system itself. So these two things, like the force and the system, is independent. So because it's external, so they're independent. However, so the frequency of the force is not always equal to the angular frequency. So you see the angular frequency takes the form of only, because omega 0 squared equals k over m, where k is a spring constant in this case, and the m is the mass of the block. So these two physics. These two values are only depend on the system itself. Okay, so now we have to distinguish these two things. So so we want to solve for x. So now we want to use our common sense. So an external force, an oscillating external force, which takes the form of sinusoidal function, is helping the system to do the simple harmonic motion. So I think we can use our common sense because the force is acting like it's oscillating. So I think because the force is guiding the system to do the motion. So I think the motion of the system, I mean the x, should have the, let's say this is f of t. So I think the x over t should take the same similar frequency of the force because it's guiding the system to do so. So I think it's quite easy to understand. Okay. So we can now write our trial solution, which is x equal to c is a constant, cosine omega t. So we are now solving for c. Okay, we substitute the solution back in our this equation, and what do we get? Okay, so to the second derivative, we get omega squared c cosine omega t is equal to minus omega squared c cosine omega t is equal to minus k over m times c cosine omega t plus f0 cosine omega t over m. Okay, so we can now solve for c equal to let's see here. Okay, we substitute k is equal to, since k over m is equal to omega squared, we can solve for k is equal to m times omega 0 squared. Okay, so c is then equal to f0. We can cancel out the cosine omega t terms. Okay, so c is then equal to f0 over m times omega 0 squared minus omega squared. Okay, then we have successfully solved for the constant that is to determine from here. Okay, then we get the eventual solution for the equation. So we see now from our intuition we can know that in this case, the force oscillation case, the frequency of the displacement is equal to the frequency of the force, because the force is guiding the system to do the motion, and its amplitude can be determined through solving the differential equation, and that is kind of an advanced case based on our first case. Okay, so because we add one more term to the equation. Okay, now next I'm going to introduce you to a new method of solving such a differential equation, which involves the use of complex numbers. Okay, first we need to be familiar with Euler's formula over here. Okay, so actually I think it's one of the most magical formulas in the field of maths and physics. Because it involves two constants, which is very important in these fields. Which is one of them is the base of natural logarithms, which is e, a constant. The other one is I, which is equal to the square root of -1. So by using the formula, we can easily convert this seemingly unsolvable thing into a combination of cosine function and sine function. So I think it's one of the most magical formulas in the field of mathematics and physics. Okay, so with this formula in mind, we can now see an example and see why it helps. Okay, so now we can write the external force, because it involves cosine function. So we see here only the sine function here involves the the imaginary unit I. So what we only need to do is that we can convert this to an exponential form, and then we only take the real part, which is the cosine part. So we can avoid this part by just get rid of this. We get rid of the imaginary part. We just get the real part, which is denoted by this sign here, RE. Okay, so we can write this. We can write this force in exponential form like this, and we take the real part. So why it helps? Some of you may find it like it's redundant. So actually, exponential functions, they have a lot of advantages. So first of all, we consider derivatives. Okay, first, like ex times ex, we take the derivative of x, and the result will be itself. So how compared to cosine and sine functions, sinusoidal functions, the derivative is much simpler. Actually, the most simple its derivative is one of the most simple rule. This is the most simple rule, in mathematics. So it's one of the advantages. Another advantage is that when we're doing like multiplication between, like cosine x times cosine y, so this it cannot be simplified. Also, if there's a phase shift like omega t minus phi, and we want to expand it because we want to isolate the omega t part, we can't do that. It's very complicated because it involve a lot of terms like this, right? However, if we want to isolate in this case isolate in exponential form, so it will be just like I omega t phi. So we can break it apart simply by multiplication rules of the exponential function. It will be just like minus. Yeah, it will be just like this. So it's much more simpler compared to the sinusoidal functions. So in most of the cases, we'll often deal with such mathematical operations. So the exponential form can significantly simplify the calculation process. So that's why we introduce complex numbers to the problem solving part. Okay, now we'll see another example. Regarding, so we solve this equation over here again using complex numbers. So let's try it and see, and again in this example we will see how it helps. Okay, we will write this over here. Right, so now we write f, which is equal to f0 cosine omega t. We write it in another form. We write it as a complex number. So it will be like this. So after we have solved this equation, we're only looking for the real part of the root. So because in this case the f in the equation is already complex, because it involves I in the exponential. So after we solve for x will also involve complex numbers. But for physical significance, we'll only take the real part of the solution. Okay, so since we have deducted just now that the frequency of the displacement will be the same as the applied external force. So the solution x will also take the form like this. Okay, and we substitute this back in. Okay, we get, like you see, the taking derivative is very important. Very simple. We just take this off to the front, and squared, because we're taking the derivative 2 times, and we maintain the rest part of the expression. So it's very simple when you're calculating, solving the equation. Okay, over m times x0, let's distinguish these things. 0 x to the and equal to omega t over m. Okay, and we divide this, cancel out these terms, and we'll get minus omega squared x0 plus k over m. K over m is obviously omega 0 squared, the angular frequency. X0 equals to f over m. X0 equals f over m omega 0 squared which is exactly the same as we calculated over here. So, but however, while I'm doing this calculation, I'm taking the derivatives, the calculation process is much more simpler in this case. Okay, now we look into the fourth case, which is forced oscillator with damping. The term damping means that we're considering friction here. So the motion will gradually decrease to zero after a long period of time. It's the most common case in reality because there's friction everywhere. So the magnitude of the friction is always proportional to the magnitude of the speed. So we give a constant here, which is c, f equal to negative c times x dot. So the sign negative means that direction of the friction force will be always opposite the direction of the motion, given its definition of friction. Okay, now we modify the equation once more. We add this term to the equation, negative c times x dot. So now we will see that we have both second derivative and the first derivative. So if we are still using the first kind of method over here, like over here, we imagine that we use this method. We have f equal to f0 cosine omega t, and we have x of cosine theta over t. So the second derivative will be a cosine function. The first derivative of x will be a sine function, and plus together. So the eventual form will be very complex if we use this method because we have both the cosine function and the sine function over here. So it's a very complicated mathematical process and will involve a lot of calculation. And so now we choose to use exponential function here, and we'll greatly simplify the process. Okay, so still we have f is equal to. Still we have f equal to f0 times e to the exponent, and always for forced oscillators, the displacement is always, the frequency of the displacement is always equal to the frequency of the force. It doesn't depend on whether it has damping or not. Since the external force is always helping the system to do the motion, so they should all have the same frequency, or the motion cannot carry on. Okay, so still the x is equal to x0 times e to the power of I omega t, and we substitute all this back in, and we successfully avoid the different sinusoidal function terms. So now we have 0 t plus I. Also, the process of taking derivatives is also very simple, because we're just removing the I omega from the exponent, and we keep everything behind it the same. X0 e times to the power of omega t plus. And these terms will cancel out. And we can solve for the x0 here. f0 over m times omega 0 squared minus omega squared plus I gamma times omega. Okay, so that will be it, because this is back in. It will be f0 Okay, so that's it, because we now again used complex numbers to solve this equation, and it turns out that it's much more simpler. And we'll discover that we have already used mathematical models to quantify the motion of the oscillators, and through graphing we can clearly see how the oscillation will gradually became. And I forgot to mention here, we're taking the real part of the solution here, because for physical significance, and we're actually graphing the function using MATLAB or something like that, so we can see how the oscillation will become after a certain period of time. And the oscillators have a lot of applications in society, the actual life. So that's why I think it matters a lot. And that's for today's video. I hope you guys like it. Thank you.